Good morning. I'm going to put one textbook problem for this video. I'm not going to try to cram 7 problems onto one video. So we'll have time to talk very carefully about this problem, which is draw a heating curve. And we're not using methanol. Let's change it up a bit and let's use methanol. And who knows, maybe we need all of these numbers, maybe not. Let's take a closer look at this problem. The heating curve is that it's that diagram where you have rises in temperature and you have a plateau, another rise as you go through your phases, gas, liquid, and solid, or you could go backwards, solid, liquid, and gas. So the first thing is understanding what the problem is asking. We have grams of methanol. Oh, methanol, if you recall your Lewis structures and chemical structures is CH3OH, okay, beginning at 170K and ending at 350K. Okay, we are not using water, so we're not going to automatically know the boiling point and the melting point for this solvent. So the melting point is 760. So that tells me we start below it. So this start is a solid. We are below the melting point. And what about this 350? This 50, see, we're above. So we're going to end up with a gas. So at some point, we're going to have to go through the liquid phase. Okay. Each of these phase transitions requires Q, requires heat, but the temperature doesn't change. So there are a couple ways that I teach this. The first way is I like to teach just drawing out each step. So for instance, if we start with a solid at 170K, oh, and we have an amount, let me just put that off to the side, grams, and we're going to go to what? To the, is this a solid? Yeah, to the melting point. So we go higher, and it's still a solid at this 176K. Okay. What do we need for that? The Q in this case is going to equal, I teach MCS delta T, but look at the specific heat capacities that they give for solid, liquid, and gas. They're in moles, okay, and they're also in joules per mole dot K. So we're not going to use M, we're actually going to use the number moles N. So that's, you got to be, a little bit flexible. Sometimes your your values given are not in the units that you're used to. Okay, but that is all solid. So we got to pick up the specific heat capacity for solid. This 105, 105, and again joules mole dot K because this is unusual. Normally it's joules per gram dot K. So what is this? We're warming up the solid and we get it to the melting point. But then we have to melt it, literally melt it. So this is called the phase transition. We're converting solid into liquid by adding heat, but the temperature does not change. So when we actually draw the heating curve, it's going to plateau. So this is called the phase transition. No change in temperature, but we do have to add heat to change the state. What is this equation? This equation is Q equals, typically it's going to be moles now. You got to pick. Is it the delta H of fusion or the delta H of vaporization? So we're going from solid to liquid. That is the delta H of fusion. And the other thing is that we're going to keep as positive. Why do we keep as positive? Because we are adding heat, adding Q or heat. See, the question was very concerned about that, or the problem was very concerned with that. We want the correct sign of the total Q. So draw the heating curve, solve for the total Q, give it in kilojoules, and have the correct sign. Okay. Again, I'm showing you two ways to do this. Well, at least two ways to set it up. So now we're in the liquid phase at 176 K, and we're heating up. But we're not heating up to 350 yet. We're heating up to the boiling point. So you're still a liquid, but now you're at 338 K. And we're back to the Q equals now NCS delta T. But now this CS has to be of the liquid. Okay, so let me try to at least color code this a little bit. Liquid. This is of the liquid. We're at the point where we need another phase transition from liquid to gas. So liquid at 338. Okay. Goes to, we're at the boiling point. So now we're going to add heat, not for the purpose of raising the temperature, but for the purpose of phase transition to the gas at 338 K. This is another phase transition. And what is this? This is using the heat of vaporization. Q equals moles delta H vape. Where's that? It's right here. Okay. It's the amount of heat needed to evaporate 1 mole of your liquid. But we're not done yet because we have to heat up to 350. Now we're heating up, I was going to say steam. Steam is for water. We're heating up the gas, methanol gas. So we have the methanol gas at its boiling point, and then we got to heat up that gas to 350 K. Q equals N, specific heat capacity delta T. So I haven't talked much about these delta T's. The delta T's are where? When you're changing the temperature of a specific phase, and where are your phase transitions? Here, where you're keeping the temperature constant, but you're adding heat to change the state of the solution, or not the solution, but of the substance. You see, it's 5 separate Qs: Q1, Q2, Q3, Q4, and Q5. The delta T, I expect this number to be positive because we're adding heat. Well, delta T is final minus initial. See, the final is higher than the initial, so you will get a positive number. Okay. Now, that's not the heating curve, but for my exam, I may not ask for the heating curve. I might just ask for the total Q, and these are the calculations you're using. But in this particular problem, they want a heating curve. So let me show you real quick what that looks like. It's not going to be to scale, and it may be a little bit sloppy, but I think we're going to put here Q on the x-axis. Sometimes that's time as it progresses, but I'll put Q there, and then temperature on the y-axis in K. Because you're starting out as a solid, so you have a low temperature right here. We're raising up to 176, so about 6 degrees, and then we hit the phase transition. And did you see how I said it's plateauing? Because the temperature doesn't change. That's what it means. It plateaus even though you're adding Q. We get everything into a liquid, and then we raise the liquid all the way to 338, and then we hit another plateau, because that's the liquid gas transition, and then we heat up the gas to 350K. So I'm not going to jot down all the numbers, but we end up at 350K, and we started at 170. So where the plateaus are, right? The plateaus are the melting point. Oh, they call it melting point. The melting point actually is the same as the freezing point, and this is the boiling point. And the boiling point is the same as, you could think of it as the condensation point. Those are your Qs. Q1, Q2, Q3, Q4, and Q5. Okay, are we ready to do some calculations? I think I am. They gave us grams, but you notice that all your values are per mole. So right away, I'm going to figure out this into moles and not worry about 48.06. The molar mass of methanol is 32.04. So we are, what are we doing? We're dividing, right? 48.06 divided by 32.04 grams. So when we divide, we'll get the inverse. The moles will be on top. Yeah, that's right. Is this number going to be what? 48.06 divided by 32.04. Oh, 1.5. 1.5 moles. Okay. And, okay, so now with all of these n's, that's where we're going to put 1.50. Alright, let's do Q1. Q1 is the raising of the temperature of the solid. Okay. Okay, N is 1.50 moles. Heat capacity. The heat capacity of a solid is 105 joules per mole dot K. So the other thing is we got to stay consistent because they want to answer in kilojoules. Can we do this in kilojoules on the fly? That would be what? That would be 105 times 10 to the minus 3. 105 times 10. Yeah, because there's less kilojoules. The number is less. 10 to the minus 3. Delta T is 6. 176 minus 170. Okay, so always keep in mind final minus initial, but that gives you a positive 6 equals 1.50 times, parentheses, 105 times 10 to the negative 3, parentheses, times 6. This will be in kilojoules. 0.945 kilojoules. That's Q1. We're going to add up all the Q's at the end. Q2, and it is positive because you are adding heat. Q2, remember Q2? That is the phase transition, and we're going to use the delta H of fusion. If we were going the opposite direction from liquid to solid, we would still use this number here, the delta H of fusion, but we would take the negative of it. But we're keeping it positive because here we're adding heat, equals 1.50, and then this is 2.2, and it is in kilojoules already. It is per mole. There's no temperature. That reminds me that I don't use delta T. I use this where the temperature is constant during the phase transitions. Okay, almost there. Now on a real test, you'd be working faster. Okay, if they ask for the Q, I would just do this part Okay, but it's going a little bit slower than on an exam because I'm explaining everything. Okay, and I'm putting annotations. 3.3, let's go with that, 3.3. Q3 equals, we are at this section right here, raising the temperature of the liquid. 1.50, so now we need the specific heat capacity of the liquid. 81.3, but remember, we want kilojoules, so we're going to do 81.3 times 10 to the minus 3. And now what is the delta T for here? 338 minus 176. 162. And this will give me the answer in kilojoules. So I have 162 already saved. Times 1.5 times 81.3 times 10 to the negative 3. 19.76. And it is positive. Q4. We are at this point in the heating curve. No change in temperature, but we are changing from liquid to gas. 1.50 for number of moles, and we're using the heat of vaporization, liquid to gas. 35.2. No change in temperature. 1.5 plus 35.2. 36.7 plus. Is that right? Yep. Is that right? Oh, I knew that was wrong. I put plus. It's multiplied. 52.8. I needed 1.5 of 35.2. Again, kilojoules for all of these Qs. Last Q, people, 1.50. We are heating the vapor from the boiling point to the final temperature. We need the heat capacity, the specific heat capacity of the gas, 48. The trick is to make it kilojoules, 48 times 10 to the minus 3. The delta T is 350 minus 338 is 12 equals times 1.5 times 48 times 10 to the negative 3. Not sure if the parentheses are essential, but just to stay safe, 0.864 kilojoules. They want the total Q with the correct sign. Let's do this. Okay, 0.945 for Q1 plus 3.3 for Q2 plus 19.76 plus 52.8 plus 0.864 equals Q for the entire process equals positive 77.7 kilojoules. Give the units, circle your answer. Is there anything unusual? Or do you notice anything about these numbers? That's pretty small, right? Because we're not really changing the temperature that much. The biggest Q actually is Q4. Whoa. Q4 is the phase transition. Why is that so large? Because look at the heat of vaporization, 35.2. Compare that to 2.2 for the heat of fusion. Okay, so it does take a lot of heat, literally 35.2 kilojoules to vaporize a mole of methanol. Okay, let me zoom out. Again, With practice, you'll get faster, and again, it will be faster because you won't be explaining every single detail. You'll just be writing down your work.